Today we're going to begin lesson 6.6. It's titled Normal as Approximation to Binomial. In other words, what we're going to do is use the properties of a normal distribution as an approximation to evaluate a binomial distribution. So first, let's review a little bit what a binomial distribution is. The characteristics a binomial distribution has is, one, there's a fixed number of trials, like we're going to flip a coin 100 times. Two, the trials have to be independent. If in one flip of the coin we get tails, that has no bearing on the next trial, on the next event. So they would be considered independent events. In contrary, a dependent event might be you're asked to pick an ace out of a deck of cards and then pick a second ace. If you don't replace that ace after the first draw, then it changes the probability on the second draw. Those would be dependent events. So for binomial distribution, the trials, they have to be independent. The third one's the really important one. Trials are classified in two categories. It's either success or failure. So if you're looking for the number of times that you get tails out of 100 flips of the coin, tails would be considered a success, and getting heads would be considered a failure. And then finally, in number 4, the probability of success remains constant. That kind of went with number 2 a little bit, that the probability of getting tails is 0.5. That never changes throughout all 100 trials that we would do. So if you remember back to doing binomial distributions, hopefully that clarifies some things. In the notations we used, N was the number of trials that we were going to perform. X was the specific number of successes we were looking for. P was a probability of success in one of the trials, like 0.5 for flipping a coin. And Q was a probability of failure on one of the trials. And that would just be 1 minus P, because they're complements of each other. So let's take a look at a question. It's a binomial problem, and we're going to use the concepts of a normal distribution to find the probability. But here's what the problem's saying. You're mailed a survey from a vacation resort. Assume the survey requested email addresses, was sent to 40,000 people, and the percentage of surveys returned was an expected 3%. Suppose the true goal of the survey was to acquire a pool of at least 1,150 email addresses to be used for a marketing campaign. Find the probability of getting at least 1,150 responses. This is a binomial problem because we either have a success, and that is the person sends in an email address, or a failure, and that is they don't. So in this problem, in the binomial distribution, we have N, the number of trials, of 40,000. We are looking for at least 1,150 responses. Our probability of success is 3%, and that means our probability of failure is 1 minus that, or 97%. And we're going to come back to this problem here in a little bit, but I want to look at why this will approach, or why we can use a normal distribution to evaluate this. Okay, so imagine that we're requesting the surveys, and we have anywhere from 0 to 40,000 people that respond. Now 3% of that, 3% of the 40,000 would be 1,200. So theoretically, if we sent this survey out to 40,000 people, we would get 12,000 responses back. That's 3%. But maybe another time we get a little less and a little more. But if we did this survey over and over again, 40,000 times, we sent out 40,000 surveys, and we did it over and over again, the number of responses are going to start to bunch up right in here, the number of email addresses that we get back. And if we did it over and over and over again, we're going to find out that although we may get some where it's very few responses, or maybe a little bit more, most of them are going to be bunched up in here. And if we put a curve to that, you would see that the number of responses that we get back, if we did this over and over and over again, would be bunched up around this 3% of 40,000. So it approaches this normal curve. All right, let's talk about the how-to now. How are we going to use normal to approximate a binomial? There's two requirements that we have to look for in order to do this. The first is that the sample is a simple random sample. So the sample has to be a simple random sample, and it has to have some sample size of n, in which the population, we know the proportion of success, which then we would know the proportion of failure. It has to be n independent trials. So basically it has to have the characteristics of a binomial, and it has to come from a simple random sample. The second requirement we have to have, and this is kind of weird, but the number of successes times the probability of success has to be greater than or equal to 5. And additionally, the number of successes times the probability of failure has to be greater than or equal to 5. This is ensuring that our sample size is large enough for us to use the concepts of a normal distribution. If you remember from the last section, when we were looking at sampling means, we said the sample size had to be bigger than 30. This is what we're doing here. We're ensuring that our sample size is going to be large enough that we can use the concepts of normal distributions. Now, if that above criteria is satisfied, okay, if n times p is greater than or equal to 5, and n times q is greater than or equal to 5, and it's a binomial distribution, then we can actually use our normal. And in order to use normal, we have to have a mean and a standard deviation. And using the concepts of this section, our mean is just going to be the number of successes, or the number of trials, times the probability of success. So if you remember back to our drawing canvas, our mean here was 1,200. And we found that 1,200 because there were 40,000 questionnaires sent out. We expected a 3% response. So 40,000 times our probability of success, 0.03, yielded 1,200. And that's why we put the 1,200 right here in the middle and considered it to be our mean. Our standard deviation then is going to be the square root of the number of trials times the probability of success times the probability of a failure. So the standard deviation is the square root of n times p times q. And these are the two values that we are going to use to find z-scores, to find individual values of x, just like we have been for the last few sections. Okay, and the last thing we need to look for is what we call a continuity correction. And it's not really that we're looking for it, but something we have to adjust a little bit, because we're taking a discrete whole number type of a variable and we're putting it into a continuous normal curve. So when using the normal approximation, we have to adjust the discrete whole number, and that's going to be our x value. We have to adjust this a little bit on our graph. So by using a continuity correction, x is actually represented by the interval from x minus 0.5 to x plus 0.5. And we're going to take a look at that here in a second on continuity correction. But this is one of those requirements that we have to have, I shouldn't say have to have, but we have to do to a binomial distribution in order to use normal properties. So when we're looking at our whole number of x, like our 1150 that was in our problem, we would have to actually look at 1149.5 to 1150.5, and we're looking at this interval on the graph. And we'll explore that a little bit more here in a second. When we use the normal distribution, which is a continuous probability distribution, as an approximation to the binomial distribution, which is discrete, we use this continuity correction. And we use it because it makes a discrete whole number, usually x, in the binomial distribution we then use this continuity correction to represent the discrete whole number by an interval. And that was at minus 0.5 and plus 0.5. So in order to illustrate this, sometimes this helps. And let me get a picture here. So let's say that our discrete whole number is 8. And 8 can fall anywhere on here. I'm just going to put 8 like right here. So if we're going to use normal to evaluate that discrete whole number of 8, we actually have to build this interval around it of 8 minus a half and 8 plus 1/2. So we really have 7.5 here and 8.5 here. And if we're actually using the normal distribution to find what's the probability that 8 occurs, we're actually looking for this shaded region. That's why we spent so much time in the earlier parts of this chapter working on finding the areas between the areas of two regions that overlap. So that would be the continuity correction for finding the probability that something is exactly 8. It would be this interval from 7.5 to 8.5. Now, what if we're not looking for exactly 8? Let's look at a different graph. And let's say that we're looking for at least 8. If we're looking for at least 8, let's put 8 right here. Then, remember we said if our discrete variable is 8, we actually are looking at 0.5 less than that, 0.5 greater than that. So here's 7.5, here's 8.5. Sorry, that's not drawn very well. So there's that interval. If we're looking for at least 8, we want everything to the right of 8. So we'd want everything here. But because we have to use this continuity correction, we can't use 8. Since we're looking for everything above it, we have to use a lower boundary of it. So at least 8 on this graph really kind of looks like at least 7.5 because we had to do this correction, turning this discrete variable into more of a continuous thought. So at least 8 would be this picture. And I'll try and, let's get rid of that 8.5 in there. It's not letting me erase. There we go. So at least 8 is going to look like this. It's everything to the right of 7.5. So let's do, instead of at least 8, let's do more than 8. Oh, use a different color this time. So if we do more than 8, if it's more than 8, do we include 8? And the answer is no. If we want to include 8, we'd say at least 8, and that's the one we just did. So if this is 8, and we don't want to include it, because we had to do this correction, we're going to use 8.5 and everything to the right of it. So more than 8 goes from 8.5 and everything right. So if we erase the 8, and I don't know if I'll be able to quite erase that line. Close enough. More than 8 is everything to the right of 8.5. How about this phrase? At most 8. If we have at most 8, are we including 8? And the answer is yes, we are. We can have at most 8, but no more. So if here's 8, and we're going to include 8, and at most means everything left of it, are we going to take this shaded graph and are we going to stop at 7.5? Or are we going to go all the way to 8.5? And the answer is, since we want to include 8, we've got to go to 8.5. So So we'd be all the way over to here. So at most 8 would be everything from 8.5 and everything left. If the phrase were fewer than 8, now we're not going to include 8. We want everything left and not including 8. So instead of using 8, we're going to use 7.5 because we want everything left and we don't include 8. So fewer than 8, this would be the picture of fewer than 8 using 7.5 as our x value. Kind of confusing, but honestly your textbook on page 303 has a very good example of this exact scenario, and this is where I pulled this. So if it is confusing and you need to see it again, look at page 303 in your textbook. Okay, so we're going to try and work that problem that we presented earlier about the 40,000 mailings that were sent out trying to get email addresses. And as we do it, we're going to introduce a procedure for how we use the normal distribution to do it. So I'm going to go back and forth as we go through this. So let's start with the procedure. The first thing we have to do is, 1, we need to verify the requirements. So, is this a binomial distribution? Is our problem here a binomial distribution? And the answer is yes. We have 40,000 trials. We have a probability of success which remains constant throughout. We have 2 kinds of responses, either success or failure. So the requirements for it being a binomial are met. The second thing would be, I'll leave it here, is n times p greater than 5. So is 40,000 times 0.03 greater than or equal to 5? And the answer is yes on that one because we got 1,200. So check. And is 40,000 times q, 0.97, greater than 5? And obviously that's going to be the complement of 1,200. So it's going to be way more than 1,200. Check. So both of those requirements are met. So we verified the requirements that it is binomial. N times p is greater than or equal to 5. N times q is greater than or equal to 5. So we're ready to move on. And step 2, hang on a second, having an issue, is we need to find our mean and our standard deviation. Remember, our formula for that was that our mean was just n times p, and our standard deviation was the square root of n times p times q. So let's go back to our problem, and we want to find our mean and our standard deviation. So our mean was n times p, which we've already done. That's 1,200. And our standard deviation is the square root of n, 40,000, times p times q. And if we punch that into our calculator, we end up with a standard deviation of 34.117. I'm going to leave it in the calculator, but that would be rounded to 3 decimal points. So now we have a mean and a standard deviation that we can use to use our normal concepts. Step 3 now in the procedure is to identify, I'm just going to put ID, identify the discrete whole number that is relevant to the binomial probability problem. So in our case, our discrete whole number that we're interested in is the 1150 number. Right there, that is our discrete whole number. So now that we have our discrete whole number, we can move to 4. And that is, we need to apply the continuity correction. I'm just going to put apply continuity correction. Remember, that was taking x minus 0.5 and x plus 0.5 and building that vertical strip around, in our case, 1150. So if we go back to our problem, and I'll have to scroll down, let's give it a little bit more room here. Here's our normal curve. We know our mean to be 1200. We know that 1150 would be a little less than that. And instead of using 1150, we're interested in using plus or minus 0.5 of that. So we're going to build this vertical strip around 1150 where we have 1149.5 and 1150.5. We're going to use one of those two numbers instead of 1150 depending on what the problem asks. So now that we've identified that vertical strip, we're ready for step 5 on here. If I can fit this in here. Try and scroll. Maybe I can give myself some room. Hang on a second. Okay, so step 5 then is, and the way the book says, let me read what the book has. It says, determine whether the value of x itself should be included in the probability you want. For example, at least x does include x, but more than x does not. So we want to determine based on the wording whether we're going to include the 1150 in our shading or not. It says then determine whether you want the probability of at least, at most, more than, fewer, or exactly. So I'm going to put, it's kind of weird, but I'm going to put shade the appropriate part of the normal curve. And that takes going back to the problem and reading it. So if we go back to our problem, scroll up to the top, and it says find the probability of getting at least 1150 responses. So do we include 1150 when we say at least? And yes, we do. And if we're looking at least, do we want more than 1150 or less than 1150? If it's at least 1150, we want more. So we've realized that we want to include the 1150. We want everything greater than that. But because of the continuity correction, we've got to shade everything to the right of 1149.5. So we shade everything to the right of 1149.5. And now we're pretty much ready to use our concepts of a normal distribution. So I've redrawn this graph on the drawing canvas to kind of make it a little bit bigger. Maybe we have a little bit of room. So the last thing we need to do in our procedure is to find the z-score and the probability. And I think most of you are probably looking at the drawing canvas right now saying, well, I kind of know what to do from here. If we need to find a z-score, our z-score is our random variable x minus mu divided by the standard deviation. And so what we're going to use is 1149.5 for x. Our mean in this problem was n times p, or 1200. And our standard deviation, I'm going to go back and find that, was 34.117. 34.117. And if we do the calculation on this, punch this in our calculator, we get a z-score of negative 1.48. And we're looking to get the area to the right of that. So we can go to our technology and we can find the area left of 1149.5 and subtract it from 1. So our z-score was negative 1.48, which gives us an area left of 0.06944. And if we subtract that from 1, we end up with an area in this part of the curve of 0.9306. So to answer the question now, it said, find the probability of getting at least 1,150 responses, given that we mailed out 40,000, our probability of success was 3%. We want to know what's the probability of getting at least 1,150. That probability is 0.9306. Okay, the last thing we want to go through is interpreting results. It says when we use a normal distribution to approximate a binomial, our ultimate goal is not simply to find just a probability. We often want to make some kind of judgment based on that probability that we get back. So when we make that judgment, we're usually looking for unusually high or unusually low events. So if we flip a coin 100 times and I have 81 tails, is that an unusually high result? And when we're using that, we're kind of using our 5% rule. So for unusually high, we say X successes among N trials is unusually high if the probability of X or more, probability of 81 tails or more, is very small. It has a very low probability of occurring. And we're going to use the 0.05 criteria. And we've kind of seen that before. And the same thing with unusually low. The probability of X successes among N trials is unusually low if the probability of X or fewer is very small. And when we say very small, again, we're looking at that 0.05. So it's not enough just to get the probability, but oftentimes we have to interpret that probability. And many times we're looking at, is this unusual? If we did get 85 tails in a flip of 100 coins, that would be an unusual event. We would have to think that there's something wrong with the coin, because the chance of that occurring just by chance is not very good. So oftentimes we're going to be asked to interpret the results that we get. Okay, hopefully you've stuck around to the end of this video. It's a little longer than most. Excuse me. But the objective was to use the probabilities of a normal distribution and to approximate and to evaluate a binomial distribution. This is section 6.6 in your textbook. So if you need to go back through anything in there, like I made sure to point out page 303 for continuity corrections. Make sure to kind of read through that. You'll see a lot of the examples that we just did if you get confused or lost at any point before we can get to class tomorrow.